Hello, my name is Maximiliano Rivera. I want to talk about the estimation of the adaptive optics time constant from telemetry data at the Paranal Observatory in the north of Chile. First, the ISO adaptive optics facility has a 8-meter telescope, 4 laser guide star, and 4 weapon sensors. Each weapon sensor is composed by a 40 by 40 apertures, and each aperture has a 20 centimeter of diameter. The RF also has a deformable secondary mirror with 1,170 actuators and operates in closed loop. The AO time constant, or commonly known as tau naught, and wind speed are two parameters that indicates the atmospheric condition and the quality of the observation. The time constant, or tau naught, is defined as the time difference for which the temporal weapon cross correlation decays by a factor 1 over e. The equation 1 shows how to compute it, and we need to know beforehand the R naught and the V star. The R naught is the fair parameter, and the V star is the effective wavefront speed, and this is computed as shown in equation 2, which is the weighted average of the apparent wind speed V and the refractive index structure constant Cn squared. So the idea is to, in order to compute the V star, we need to know the velocity at each height and the Cn squared at each height. So if we use the Taylor hypothesis of frozen flow, we can split the atmosphere in several layers. So we need to know the apparent wind speed of each layer and how much contributes to the atmospheric condition or the turbulence. Yeah. Some consideration of the method is that the RF use closed loop data, so we need to rebuild the pseudo open loop slopes. Also, we need to remove the tip tilt, and we do this by applying finite difference to the slopes. Moreover, instead of using spatio-temporal cross correlation, we use a single convective map, and we estimate turbulent layer apparent speed by using an automatic peak detection method. And we aim to detect the simultaneous layer detection between 3 and 50 meters per second. The method is split in 3 parts. The first one is the pre-processing the data. The second one is building the correlation maps, and the third one is when we do the peak analysis. The first step, when we pre-process the data. Here we do the tip tilt removal. We compare 2 approaches. The first one is as it is shown here that we remove it by compute the average extraction, and we can see that the result of this operation is that we have here a wider and broader peak, comparing with the tip tilt by using finite difference, as shown in this figure, when we can narrow the peaks and separate the layers. So we can see that instead of having a wider peak, we have 2 different peaks here. And as we're going to see, each peak corresponds to a given layer. Each peak corresponds to a given layer. And this is because we, in step 2, when we are going to build the correlation maps, we use the Taylor's frozen flow hypothesis, which is that the atmospheric turbulence is located in thin horizontal layers moving with constant speed. Here we have in this figure a simulation of phase distortion at a time t, which is the blue circle, and a time t plus tau, which is the dotted circle. If we compute the correlation between these two frames, the frame at t and t plus tau, we're going to obtain a map where a peak is going to be located at b times t, which is the displacement. Yep. And this can be seen in the figure before, where this peak is at a given position and computed at a given time, which is 70 milliseconds. So with this information, we can know the velocity of this peak, which is the velocity of the layer. Yeah. Also, the height is going to give us the weight. So if we have more layers, we're going to have more peaks in here. And in order to detect fast and slow layers, we need to select different taus. So here it is shown a non-uniform tau selection, and the aim is to detect layers from 3 to 50 meters per second. So first we analyze the fast layers here using a small tau. Then we analyze the mid-speed layers using a mid value of tau. And finally, in order to analyze the slow layer, we use a larger value of tau between 150 milliseconds to 250 milliseconds. So in order to analyze the slow layers, we need to wait more time in contrast to the fast layers. So the difficult part here is that we're going to have tons of maps to analyze. Each map is going to give us a peak position, which means a velocity. Yeah. So we need to analyze all of this map, which is computationally expensive, and also we need to do some tracking of the peaks, because we don't want to detect two same peaks which are the same. And this is solved by making the convective correlation map, which is shown here, which is the idea is to use all of those maps to build only one map, which its axis is the speed. Here we can see that using real data, we can see that a peak here has a position and an amplitude. The position is the wind speed and the amplitude is the weight. So if we have several layers, we can see that each frozen flow layer produces a peak at a given position, which is the velocity. So if we have several layers, we will have several peaks in only one map. So we only have to analyze one map in order to compute the wind speed. Then, in order to find the peak, we develop an automatic peak detection algorithm, which is split in two parts. The first one is smoothing. It's a smoothing process, and the second one is a maximal regional detection. Here we can see in this figure two-layer simulate data, which the first layer, which I'm pointing at, has a velocity of 11.3 meters per second and a magnitude of 70%, a weight of 70%. The second one has a 50.7 meters per second, and the third one 33.3 meters per second. And this one has a 5% of contribution. Yeah. So the first step is to smooth the CCM. Yeah. And this enables us to separate or isolate the layers. So here we can see that we have three different layers, and then using a maximal regional detection, we can estimate the three layers and also the height of these layers are the weights. And so with this, we can compute the wind speed, and then we can compute the tonal. Some results here in this graph, it's analyzed the results of applying our algorithm to the available data set from the IRF, and we compare the estimation of the 4 reference sensors. So here it's presented a box and whisker diagram, and we can see that the dispersion of them are quite low in comparison with this one, and we can see that it's quite consistent, the estimation. This is for the wind speed. Also, we have here for the tonal estimation, and as I was saying, the result between the reference sensors are quite consistent, and in particular cases of different layer detection, there is an increase of dispersion for large tower. So here, as we can see, we have this for the wind speed. We have a dispersion. This translates to a quite important dispersion when estimating the tonal. So, in order to finish, the use of finite difference applied on the slopes brings sharper and thinner peaks, which enables us to easily detect peaks. Then the use of convective correlation maps increase the level of SNR by making one map, and also we only have to analyze one map instead of tons of maps. And the automated peak detection algorithm find out every peak from the CCM, as I showed. For future work, there is a work ongoing for comparing the performance of this method with the mass dim instrument, which is the instrument that measures the tonal and the wind speed, but it's computed at zenith. So the idea is to compare them and see the accuracy of our algorithm. So in order to do this, the algorithm is going to be implemented in the ARF at Paranal. Here we can see the acknowledgement, and thanks for listening. And here I can show the bibliography. Thanks.